Hi, I'm Mark Bird, the Director of the Magnet Science and Technology Division here at the National High Magnetic Field Laboratory. And we're in the Resistive Magnet Shop, where we build the world's most powerful DC magnets. We can show you how a basic resistive magnet works. This is a piece of copper wire that's been wound on a piece of steel. And then there's a battery in the circuit. And when the battery's put in, you have current flowing through the wire. It makes a magnetic field in the center. The magnetic field magnetizes the iron, and then you can pick up paper clips and things like that. That's a very small magnet. And the field at the tip of that piece of iron is about 0.01 teslas. The magnets we make in this shop provide fields as high as 30 teslas. To make a magnet that powerful, you can't simply make one like this bigger. And there are two reasons for that. One is it would overheat, and one is it would rip itself apart. So to build a more intense magnet, you have to deal with the heat.
Where does heat come from?
Anytime you put current through a piece of conductor, a copper wire, it generates heat, the same way an electric stove makes heat or a light bulb makes heat. So instead of using copper wire that's insulated, we'll use copper sheet metal. And so we have bitter discs here. These were first developed by Francis Bitter in the 1930s at the Massachusetts Institute of Technology. He used copper sheet metal, stamped lots of holes in it. He made insulators with the same cooling hole pattern, and by stacking these in an alternating conductors and insulators, you can make a helical pattern. You put current through it, high current through it, you'll get a high current density, you'll make a magnetic field in the center. But now we can pump cold water through all these holes and get a velocity up to 20 meters a second, which is about 45 miles per hour, and keep the magnet from melting.
The water goes into that big hole in the middle?
No, that's the hollow center of the magnet called the bore, where the magnetic field is strongest and where the scientists put their experiments. The water passes through these elongated cooling holes. This type of bitter disc, invented right here in Tallahassee, is now used at magnet labs all over the world.
Okay, so the cold water keeps the magnet from overheating. What keeps it from being destroyed by all that power?
In this magnet, the current is flowing around in circles. The magnetic field is perpendicular to those circles, and so there's a magnetic force outwards everywhere in the disk. And so to make these hold themselves together, we have to use very high strength copper alloys. So these disks, the highest field ones, are made from an alloy of copper and silver that's actually stronger than the steel that you see in the beams behind me, yet it has electrical conductivity 75% that of pure copper. So by combining this very high strength material, making these rings of conductor, providing a cooling system, we're able to get to much higher fields than you could with a simple wire wound coil.
The shrinking quarter is one of the most popular attractions at the Maglab's annual open house. And no wonder.
Combines all the good things of a science project. Light, flash, certain sense of danger, noise, excitement, and yet proves a very important law of basic physics and does something which could not be done in any other way. And it uses a magnetic field.
This cool experiment shrinks a U.S. quarter down to the size of a dime in just 1/1,000,000th of a second. How do we do it? With a powerful machine customized here at the lab, the interplay of electrical and magnetic forces, a handcrafted coil, and the same 120-volt outlet you use to plug in your toaster. First, let's take a look at that coil. It's actually a type of electromagnet. When electricity runs through it, it generates a magnetic field. To make this specialized coil, you start out with
14 gauge copper wire, and we put 10 turns on there.
The magnetic field will be strongest in the middle of the coil, so that's where the quarter goes.
So we use a couple pieces of PVC pipe to hold the quarter in the center of the magnetic work coil. We stack it like that, and then the next step is to tape it together. It takes a while to make each one, and the more precisely it's made, the more perfect the coin comes out. Then we tape that in place, and there's our finished coil.
The coil is ready to go into the shrinking machine, which in a nutshell works like this. When it's plugged into a regular outlet, the machine charges up a capacitor, a kind of battery that stores electricity. In this case, it holds upwards of 7,000 volts, way more than your familiar AA. Some 100,000 amps, enough electricity to power 1,000 homes, will shoot through the coil, way more than it can handle. An explosion ensues, spraying shrapnel through the air and creating a ball of plasma as hot as the surface of the sun. These heavy blocks in a bulletproof box shield spectators from the blast, and for good measure, a bungee cord.
We're going to bungee this box down because the shock wave produced inside there could lift this box right off the platform.
Now it's time to charge up the capacitor.
The whole process takes about 40 to 45 seconds. 3,000 volts, 4,000 volts, 5,000 volts, 6,000 volts, 69, holding at 7,000.
Now Russell flips the switch. Pay attention. If you blink, you'll miss it.
Ready? Okay, here we go. All done.
Did you blink? Here it is again.
Okay, here we go. All done. And there's a lot of smoke and stuff in there right now. You'll see that our coil is gone. It's vaporized and it's turned into thousands of little pieces of fragmented wire from so much energy going through that wire. So we're going to open it up and take a look at it here. There's our shrunken quarter. Looks like we've got a really nice shrink on that one. Got a lot of detail to it.
The coil has been smattered to smithereens. The quarter, however, is safe in its little nest. The explosion that blew the coil outward also forced the quarter inward. So the quarter retains the same mass, but its diameter has shrunk by a quarter, no pun intended, while its width has grown. So how do you account for this magic trick? The very high current in the coil generates a very high magnetic field in just a fraction of a second. Changing magnetic fields can also induce electrical currents in nearby conductors. This is called electromagnetic induction. So the quarter, made mostly of copper and nickel, begins to conduct electricity too. Because those charged particles are moving through a magnetic field, they experience a force known as the Lorentz Force. The Lorentz Force pushes those particles inward from the circumference of the quarter toward its center. The stronger the current you put into the coil and the more quickly you put it in, the stronger and quicker the magnetic field, the greater the Lorentz forces, and the more the quarter will shrink. From Isaac Newton we learned that to every action there is an equal and opposite reaction. In this case, the reaction to the powerful Lorentz forces pushing inward is the coil exploding violently outward. If you don't get a bang out of science from this demonstration, you won't get it from anything.